Okay guys, before we get started on today's lecture, what I want to do is do a quick review on the material that we covered a couple weeks ago in class. Remember that we established something called the solar nebula hypothesis. And this is a hypothesis stemming from evolutionary theories, proposing that the planets in our solar system formed with the sun. Okay, so it formed naturally with the sun. And the hypothesis states that planets form in the rotating disks and gas and dust around young stars. Astronomers then try to test this hypothesis, and they do this using four things. One is the revolution and rotation of planets. Okay, so we talked about how most of the planets, most of the satellites around those planets orbit in a counterclockwise rotation. And this goes along with the rotation of the sun around its axis, which is also counterclockwise. And so this inherent property of rotating counterclockwise is one of those ways that we test the hypothesis of the solar nebula theory. The second is the types of planets. So up here on your screen you have the first four planets, the innermost, Mercury, Venus, Earth, and Mars. And those are our four terrestrial planets. The second type is the Jovian planets. Those are our outer planets. And we're going to establish the differences between those two later on in this lecture. The third piece of evidence that we look for when we test this hypothesis is space debris. These are things like comets, asteroids, and meteoroids. What I would like you to know for the quiz on Thursday is those names of those threes, but also what's the difference between a meteoroid, a meteor, and a meteorite. Know why we give those different names, or how we establish those different names. The fourth piece of evidence that we used in order to establish this theory, or back up this theory, is the age of the solar system. Okay, and the way that we do that is looking at different things within the solar system. We can look at meteorites and carbon date those. We can look at the lunar rocks from the Apollo missions and date those. Another one that's more recent is testing the surface of Mars with the Curiosity rover and testing that. We've established that the sun is about 4.5 to 5 billion years old. And through carbon dating some of these materials within our solar system and some on Earth, we can also establish those that date and around that time as well, furthering our evidence of the solar nebula hypothesis being accurate. So what we're going to start off with today is talking about the four terrestrial planets. And when we look at these four terrestrial planets, we can see that they are all made up of rock and metal. What I mean by rock and metal, I don't mean necessarily some specific compound or specific element of rock and metal, but we talk about it in a general term. So a metal could be, gold, it could be iron. Iron, of course, is the most common of the metals found in the planetary bodies. But don't get confused, or don't narrow your thinking to just being iron or granite, for instance. Between the crust, okay, so the surface of these bodies, and the core of these bodies, we have what's called a mantle. And that's your only vocab term that's within this lecture. The mantle is a layer of dense rock and metal oxides that lies between the molten core and the surface of a planet. Remember that we believe, or astronomers believe, that the planets formed along with our sun about 5 billion years ago. So during the formation process, there was a period of intense comet and asteroid bombardment that peppered the young planets, okay? And these created craters on the surface. This period is known as the late heavy bombardment. And we use this late heavy bombardment as a key factor in the timeline of the evolution of the planets themselves. So Venus, Earth, and Mars all have atmospheres. And when we talk about these atmospheres, we're going to talk about a planet's ability to have an atmosphere. There are two things that an atmosphere is dependent upon. One is the physical characteristics of the planet itself, and that means the size and temperature of the planet. The second piece that's important to establishing an atmosphere is the geological history of the planet. So physical characteristics and geological history. Let's talk about Mercury. Okay, Mercury is the closest planet to the sun. Mercury has a surface temperature of 872 degrees Fahrenheit. Very hot, okay? On the surface that's facing away from the sun, that is negative 300 degrees Fahrenheit. So extreme differences, okay? So imagine this planet where half of it is 872 degrees Fahrenheit and the other half is negative 300 degrees Fahrenheit. Crazy. Mercury is heavily cratered, okay? Mercury does not have an atmosphere, and that's because it is too small to retain an atmosphere. Remember, temperature is another factor in retaining an atmosphere or having an atmosphere. And it's believed that Mercury has lost much of its internal heat. So even though the surface is capable of getting very hot, it loses a lot of heat, probably because it doesn't have an atmosphere. It's probably a result of that, which is kind of ironic, right? That temperature plays into the factor that we have an atmosphere, yet temperature is also oftentimes related to the atmosphere itself. Mercury does not have any satellites. I use the term satellites quite often rather than moons. It's just something that is ingrained in my brain. So no, when I say satellites, I mean moons. Let's look at Venus. This is Venus up on your screen right now. This is showing the surface of Venus. Venus has a surface temperature of 864 degrees Fahrenheit. That's an average temperature. Venus has an extremely thick atmosphere. And when I say thick, I mean very dense, not necessarily in height. It doesn't have any oceans, and it is heavily volcanic, so a lot of its surface is volcanic. This is one of those volcanoes that is on the surface of Venus. And the second surface feature I'm going to show you is a crater. This is a radar image of a crater on Venus, which is an interesting feature to have. And you think about how craters are made. They're made by something from outer space hitting the surface of the planet. And we know that with an atmosphere, oftentimes those space debris are burned up within the planet, or burned up within the atmosphere, and rarely reaches the surface of the body. But in this case, we have something very large that hit that planet and impacted it. Venus also does not have any satellites like Mercury. Venus is very similar in size to Earth, and so we might expect it to have similar characteristics, but because Venus is 30% closer to the Sun than Earth, then we have a very different environment. Its atmosphere is made up 96% of carbon dioxide and 4% nitrogen, argon, sulfur dioxide, sulfur acid, hydraulic acid, and hydrofluoric acid. Not something we necessarily want to breathe. Its atmosphere is 90 times more dense than Earth, and to put that into some perspective, that's 10 times more dense than water. So imagine trying to breathe something 10 times more dense than water. That'd be crazy. Earth's atmosphere, for example, is 1,000 times less dense than water. So very opposite spectrum. The reason that Venus has such a thick atmosphere, or dense atmosphere, is a direct result of the greenhouse effect. So greenhouse effect is when we have sunlight that filters down through the clouds and warms the surface. So we've got this radiation coming in from the sun, but when it reflects off of the surface of Venus and tries to escape out the atmosphere, it cannot. So the sulfur dioxide and water vapors within the atmosphere, trap any radiation that would be trying to escape the surface of Venus. Also, because Venus's atmosphere is 96% carbon dioxide, it makes this greenhouse effect even more effective. So it makes it more severe. So one of the main causes of this dense atmosphere is the lack of water on Venus. There's a little diagram, half of Venus on your left and then Earth on the right. So while it may have had small oceans in the beginning of its life, because it's so close to the sun, a lot of any water that could have been there would have evaporated away or dried up as a result of the warmer climate, because of this greenhouse effect. So we just kind of have these bad conditions for Venus that just doomed it. So let's turn to our third terrestrial planet, that's Earth, and we're very familiar with Earth, obviously. Earth can actually have a surface temperature that ranges from negative 60 degrees Fahrenheit to 120 degrees Fahrenheit. Reasonable for humans. Maybe not the negative 60. I wouldn't want to live in negative 60. Earth's crust is geologically active, okay, and we have evidence of that through earthquakes, volcanism, and mountain building. And these are all linked to the motions in the crust and the plate boundaries. So here's our plate boundaries, and I apologize for this being so blurry. It's the best image I could find. These red lines are where our plate boundaries are. Of course, these aren't the only place where we have earthquakes or the only places that we have mountain building. You can see we have, the Appalachians, of course, mountain building effects, but the reason that we have these features is because of tectonism and an active planet. Earth has an atmosphere, and it's believed to have been formed hot. Okay, so the atmosphere was formed at a high temperature. Because it was formed at a high temperature, gases such as carbon dioxide, nitrogen, the water vapor, the stuff that has doomed Venus, would have been cooked out or evaporated out of rock and metal as Earth grew. So it was evaporated out of the surface of our planet. The atmosphere we breathe today, I'll go back here, sorry, is a result of the production of oxygen by outgassing and the green plants. So the fact that we have trees on Earth is or the fact that we have a clean atmosphere that we can breathe is a result of all the trees and such that we have on our planet. We have one satellite, as you know, that is our moon, and it's believed to have been formed by the Large Impact Hypothesis. Okay, so during that hypothesis, or what that hypothesis says, is that while Earth was a proto-Earth, so not quite a planet, a Mars-sized planetesimal or Mars-sized object came in and smashed proto-Earth. As a result, a bunch of debris was ejected into space, and that debris eventually formed our moon. The moon was then subjected to a late heaven bombardment, okay, so that's why it's so heavily cratered. And it created this lifeless cratered surface. So that late heavy bombardment is that key timeline to our moon looking like it does. Not all satellites are natural, so we consider the moon a natural satellite. But some satellites from other planets, for instance Neptune, these could be captured satellites, or captured asteroids, or captured comets, along the way. They just got pulled into that gravitational field. Earth actually does have some mini moons, okay, and they're a few feet across, so not very big. And they orbit Earth for about a year or less than a year before they escape. So there's some objects that are really tiny that Earth is capable of capturing, and then they eventually leaves Earth's orbit. Our last terrestrial planet, this is Mars. Mars has a surface temperature of negative 67 degrees Fahrenheit, and that is an average temperature at a winter pole. So let's say the North Pole is in winter, and you can see that up here with some ice cap. That pole is capable of getting negative 207 degrees Fahrenheit. Extremely cold. And then in this image, the south is in summer, and that's about 80 degrees Fahrenheit. So, not too bad, pretty comfortable. The surface of Mars is cratered. It also has volcanism, and then has some plains, like some prairies of sorts. Mars has an atmosphere, although it's very minimal. It contains 95% carbon dioxide, 3% nitrogen, and 2% argon. It makes the composition itself is very similar to Venus, but it's extremely thin. So it's less than 1% dense as Earth's atmosphere. Extremely low density. The low water content in the atmosphere, so not really water vapor in that atmosphere. And the polar caps that are composed of frozen water ice. These are, you can see this here, these are the polar caps that I was mentioning in that previous slide. So we have this regeneration of the atmosphere that in summer the carbon dioxide vaporizes from the surface and adds to the atmosphere, while the winter pole freezes out the carbon dioxide and brings that to the surface. So, surface and then atmosphere, surface and atmosphere, all generated by that heating of the summer and winter. Liquid water cannot survive on Mars, and this is because the air pressure is too low. So early in history, this may have been different, but if the atmosphere had once been thicker, liquid water could have flowed on the Martian surface. And this is something that's being investigated by a lot of planetary scientists to see. There are fluvial channels that are possible that are believed to be on the surface of Mars, and so is it. Do we have proof that at some point Mars had some flowing water? Who knows? Mars has 2 satellites, Phobos and Deimos. Phobos is 150 times smaller than that of our moon, and Deimos is 280 times smaller. Very small. Although classified as natural, these may be, they're probably captured asteroids from the asteroid belt. Phobos, so this is an artist rendition, not an actual image. This is an actual image of Phobos. And it orbits so close to Mars that eventually it'll get sucked into Mars's gravitational pull, and eventually it will break up because it's not a very big satellite. It will break up and form a ring around Mars. So let me go back to this one. Okay, so this is that's Deimos there. That's the 2. Here's the proximity. Okay, and this is that ring image I wanted to show you. So this is projected to happen in about 100 million years. Not something we'll see, but interesting to know that Mars could possibly have rings at some point. Let me go back and show you. Here's our Deimos, an actual image of Deimos, and then the 2 satellites with Mars as in the on the left. So let's talk about the Jovian planets. So according to the solar nebula theory, or solar nebula hypothesis, they're interchangeable almost, the Jovian planets began to grow by the same processes that build the terrestrial planets. Okay, so we've got this debris that's orbiting counterclockwise around the sun, and they're all drawn in together, and eventually forming planets. The theory is that the Jovian planets grew faster, okay? And the inner, so within the inner solar nebula, the nebula within the asteroid belt, or also known as the ice line, only metals and silicates could have formed solids. So the terrestrial planets grew more slowly. The Jovian planets grew more rapidly and quickly, and became massive enough to grow by gravitational collapse. So remember when we talk about the star formation, eventually stars will form, they form out of that cloud, and eventually they'll start collapsing under the gravitational pull of the atoms, okay, that's forming that star. And so when we get up to a planet size, to a body that's planet size, and we get that planet size large enough, we can have the same type of formation. So Mercury, Venus, Earth, and Mars were not necessarily formed by that gravitational collapse, and so they grew more slowly. But these outer planets are large enough, they have enough material that they would have been pulled in by gravitational collapse. The Jovian planets must have grown to their present size in about 10 million years. This is before the sun became hot and luminous enough to blow away the gas and dust in the solar nebula. All planet growth must have ended with the last of the solar nebula being blown away by the time 100 million years had passed. Okay, so there's this time frame of the sun forming, the sun becoming a star, all this material being surrounding that sun and forming these planets. And then remember, we talked about the sun becoming luminous enough, and it's blowing out, or projecting energy out that's blowing out the rest of the material, and all the planets should have been formed within that timeline, or by that time. So the solar nebula theory, or solar nebula hypothesis, has been successful in explaining the formation of the solar system. But there are there's some problems, and the Jovian planets are pretty much the troublemakers within this hypothesis. The two observations of the Jovian planets that are forcing astronomers to expand and revise their theories of the planets are: one, the majority of the exosolar planets found around other stars have the same mass as the Jovian planets. So they're very similar in mass to these Jovian planets. So why is it that, a lot of the planets that we find around other stars are Jovian in type and not terrestrial? There could be, some very logical explanations. One, that the terrestrial planets are obviously a lot smaller than these Jovian planets, so maybe we're just not seeing them. And that's an important fact, is maybe the terrestrial planets, and we have found some recently, but maybe they're just too small for us to detect. The second problem with the Jovian planets that's causing a revision of the solar nebula hypothesis is that the gas and dust around newborn stars does not last long. Okay, within, astronomical terms. We're talking about 100 million years. That's not a long time within astronomy. So these dust gas disks, okay, that form around the young stars, are observed to evaporate by the intense UV radiation from nearby hot stars. Okay, so remember, stars form in clusters, and so if we talked about this a little bit, where you have a young star and you have another hot star growing next to it. Well, that hot star growing next to it is also putting out radiation and heat, and it's going to also move around any kind of the material that's forming around these stars. So that's one of the other problems with these Jovian planets. Mathematical models show that massive planets may have been able to form from the gas without first forming a dense core by accretion. Okay, so accretion is that formation or that gathering of material within that gas and dust around a star that forms the terrestrial planets. But within the Jovian planets, the accretion process does not fit the time frame necessary in order to form these Jovian planets. So new theories are projecting that accretion is not a necessary thing or necessary process for the formation of the Jovian planets or planets themselves. So let's talk about the Jovian planets themselves, or in particular. Jupiter and Saturn are known as our gas giants. And while Uranus and Neptune is classified as, are classified as our ice giants, and these are based on the chemical composition, okay? So they're all gaseous. You cannot stand on the surface of Uranus or Neptune, but by composition they're called ice giants. So ices being that their composition are commonly found in ice. All four planets, Jupiter, Saturn, Uranus, and Neptune, have a lot of moons. So in general, all the Jovian moons or satellites gravitationally interact with their parent planet, and most are geologically active, or at least were at some point in time. Let's talk about Jupiter. Jupiter has a cloud temperature of negative 234 degrees Fahrenheit. Very cold temperature for those gases. It has 67 natural satellites, and it also has a ring system. So I'm going to give you some numbers of satellites, and this probably differs from your textbook. And when I give you these numbers, it's the numbers of satellites or moons that have been named. So when I say it has 67 natural satellites, it may have more, in your textbook may mention more, but 67 of them have been named and identified. The four major satellites that we know are the Galilean satellites. Okay, this is something that we studied earlier in class. These are Io, Europa, Ganymede, and Callisto. Io, over here on the left, is the size of our moon. Its volcanic surface. It has a very volcanic surface. Europa, right here, is the size of the moon as well, approximately. It's likely rocky with an ice crust, and it likely has folds or mountain structures. The third is Ganymede. Ganymede is the largest moon in the solar system, and it's 8% larger than that of Mercury. Can you imagine a satellite or a moon that's larger than one of our planets? It's rock and ice, and it has a grooved terrain. That's all by geology. And the last is Callisto. Callisto is half the size of the moon. It's rock and ice, and it's heavily cratered, and also has this very dark surface, which is really interesting. I mentioned that Jupiter has a ring system. This is Jupiter and then the sun illuminating it behind, so we can see its rings here. Jupiter has an equatorial radius of about 55,000 miles. Okay, so from the center to out here is 55,000 miles. Its ring system extends from 174,000 miles. Okay, so that would be here, 174,000 from its center to I have that backward. This is my 55,000 miles here, and then out here, the tip of that, so from the center out, the tip of that ring, or the edge of that ring system, is the 174,000 miles. that means the extent of these ring system is 119,000 miles. A pretty large ring system. The main ring, which is about 100 kilometers thick. Okay, so when I talk about thickness, I mean here, thickness. And it was created by meteor impacts on small nearby moons. So, meteors are hitting these moons, maybe during the late heavy bombardment, and shooting out debris into space. That debris does not escape Jupiter's gravitational field and instead forms rings around Jupiter. Let's talk about Saturn. Saturn has a cloud temperature of negative 292 degrees Fahrenheit. So not much cooler than Jupiter, but extremely cold. There are 62 natural satellites of Saturn, meaning that there's 62 satellites that have been named that formed during the process of Saturn formation. And of course it also has a ring system, and Saturn's known for its ring system. The two most commonly talked about moons are Enceladus, okay? So first is Enceladus. Enceladus is commonly known for its tiger stripes, and I mentioned tiger stripes one time in lab. And these are plumes, okay? And they're plumes within the lithospheric crust of Saturn. It's called an icy satellite because it's mostly made of ices. It has an ice crust, as you can see here. And it has a diameter of 318 miles. So you could fit Enceladus in the state of Washington. The second most common satellite, which is one of my favorites, is Titan. And Titan is most commonly known for its Earth-like features, and Shannon really did a phenomenal job explaining Titan, so I really don't feel like I have to go over too much. But, some of those features are mountains, dunes, lakes, seas, and a cryovolcano. It's also known as an icy satellite, and it has a diameter of 3,202 miles. So it could fit roughly within the United States, but a little bit more. Here's its rings, okay? So Saturn's ring system spans from 42,000 miles. So from its center, it starts about 42,000 miles from its center and goes out to 300,000 miles. So from this point to out here, the last point, there's about 258,000 miles of rings. So the thickness of these rings varies from 2.7 feet to 90 feet. It's crazy how thin these rings actually are. There are also several moons that orbit within the ring system. And so, let me go back. I guess I don't have a slide of that one. But these satellites include Mimas, Enceladus, so Enceladus, this one here that we talked about, Tethys, and Dione. And, there's debate on whether or not these satellites feed the ring system or the ring system formed these satellites. Our third Jovian planet is Uranus. Uranus has a cloud temperature of negative 364 degrees Fahrenheit. So we're going, another 100, about 70 to 80 degrees Fahrenheit colder. There are 27 natural satellites that belong to Uranus, and it also has a ring system, as you can see in this image. These are the 5 most prominent satellites, and these are all taken with the Voyager spacecraft. This is Miranda, Ariel, Umbriel, Titania, and Oberon. What makes Uranus interesting is that it's a common type among exoplanets, so it's considered an ice giant, which is often what we find around other stars. And the fact that it has believed to be natural satellites is really interesting because, we could have a planet right here that is very common in the universe that we could study and study not only it but its satellites and its system and see well, how did that system form, and relate that to other systems within the universe that we can't reach. Its ring system. So this is an image showing its ring system, obviously not in visible wavelength. This ring system spans, so right here from its center would be approximately 26,000 miles, and it goes out to 61,000 miles out here. So, about 35,000 miles difference, much smaller than Saturn. Its thickness is unknown. We don't know. Your Voyager is the only spacecraft that has been out that far, and so we don't know why they're so thin. Sorry about that pause there, guys. So the last planet that we need to cover is Neptune. This is that image of Neptune. It's a really pretty planet. Neptune has also only been visited by the Voyager mission, and this was visited by Voyager 2 in 1977. So any images I'm going to show you either by the Hubble or by Voyager 2. Neptune is the most popular of Neptune's satellites. It has 14 natural satellites, or I say natural, you can't see my air quotes, but there are air quotes around them. And the most popular of these satellites is Triton. Neptune also has a ring system. That's part of that, or is important to that system as well. This is Triton. Triton has a radius of 841 miles, and that's about 3/4 of our moon, to put that into perspective. The reason I quote-unquote natural, and when I talk about Neptune's satellites, is that Neptune could have captured all of its satellites, and so, whereas the satellites of Uranus probably formed along with the planet, Neptune probably, it may have had satellites that formed with it, but they were likely shot out, and then Neptune gathered these objects from space debris and things like that, or maybe it stole some moons from another planet. Here's its rings, so you can see this is where the planet would be here, and then the sun shining behind it, giving us an illusion of its, or an image of its rings. The rings span from 26,000 miles, so say here's the center, 26,000 miles is where we start that ring system, and it spans to only 39,000 miles, so this ring system is only 13,000 miles. I say only, that's a lot of miles, but compared to the other ring systems in our solar system, not very wide at all. These rings are clumpy, and they have prominent arcs. They're also reddish in color, so if we were to look at them in the visible wavelengths, they'd appear red. So let's talk about how these giant planets form their satellites. We talked about a little bit with Neptune, how it likely stole satellites from other parts of the solar system. And I've alluded to how they form satellites when I've talked about the formation or natural satellites. So much how planets form around the sun within that solar nebula, or that, not solar nebula, but planetary nebula. We would have like a moon nebula or satellite nebula that formed around these planets as they formed, and you would have had these natural satellites forming around these giant planets. This is not, of course, as we talked about, this is not how the moon formed. The moon didn't form from a moon or satellite nebula around Earth, and this is not how I don't want to say Dione because that's one of Saturn's moons, but how the moons of Mars would have formed either. we mentioned how those were likely captured asteroids. So these are around these planets that are large enough to have had a satellite nebula that would have formed these natural satellites. Let's talk about Pluto, because even though Pluto is not a planet, it's still very cool. Pluto has a surface temperature, an average surface temperature of negative 380 degrees Fahrenheit. Pluto has 5 natural satellites. So even though something like Neptune, a planet like Neptune that's huge, probably doesn't have any natural satellites, Pluto, not even a planet, has natural satellites. How cool is that? So this is of course from New Horizons, this image here. And these are the moons of Pluto. Okay, so we have Charon. Charon is here. There's not a very, well, not a great image showing all 5 of them with Charon in full scale. So this is Charon, okay? Just a little piece of it. It is 750 miles in diameter. It's not huge. That's Charon there. Incredibly geologic. Look at all those grooves and craters and just super interesting body. We have Styx. Yes, this is one of the best images we have of this planet. Nix, Kerberos, and Hydra. Even with New Horizons flying as close as it did to Pluto and to Charon, we still couldn't get great images of its other 4 satellites. It's possible that these satellites formed by impact. Pluto is obviously not large enough to have formed satellites by, say, that satellite nebula, quote unquote. I'm making that term up. That's not a real term. But they could have formed by something like similar to that of the moon. There's impact with Pluto, and they formed these satellites. So why is Pluto no longer a planet? Okay, so back in 2006, not that long ago, right? 10 years ago, astronomers established 3 criteria to making a planet a planet. The first is that it must orbit the sun. Pluto does that, okay? A planet must orbit the sun. Makes sense? A moon does not orbit the sun. A moon orbits that planet, that parent planet. So not a planet, obviously, but the Pluto does. The second criteria, and you want to know these criteria, is that the moon, that it must be large enough, the planet must be large enough for gravity to form the planet into a round sphere. Well, look at this image. Is Pluto a round sphere? Yes, it is. So it fits that criteria. The third criteria is that the planet must have cleared out other objects out of the way within its orbital neighborhood. So it must not have any additional debris in its orbit, along its orbit, in order for it to be considered a planet. So if we think about, say, Earth along its orbit, there's nothing else orbiting in Earth's orbit. It's just Earth. Pluto does not fit this criteria. There are other objects that orbit within the neighborhood of Pluto's orbit. Pluto does not gravitationally pull them in or anything like that, and so therefore it rules Pluto out as a planet. So that last and third criteria is the doomer for Pluto. So look these over. Remember the things that were talked about. I pointed out some key things. The planetary criteria, for instance. Those are important to know for our quiz. Let me go back a little bit. What's a mantle? That's one of our vocab terms. That's really important. Don't get lost in the surface temperatures of these planets. You don't need to know those numbers, but you need to know that in order for a planet to have an atmosphere, those terrestrial planets' atmosphere, what are the criteria, the 2 characteristics or 2 criteria in order for that planet to have an atmosphere. That's our physical characteristics, meaning size and temperature. That's why I was giving you some of those surface temperatures. And then the geological history of that planet. Is something crazy happening to that planet's surface that's causing that surface to not have an atmosphere, or to have a crazy atmosphere like Venus. Venus has a ton of volcanism, which feeds into that very dense atmosphere. So those are some of the key components to this particular lecture that I need you to know for the quiz on Thursday.